Good morning, everyone. My name is Pius Nyanumba, and I come from the University of Nairobi, and my project was on Gaussian process modeling in rotation measure synthesis. And I will start by introducing you to rotation measure synthesis. This is the tool used by astronomers to separate different sources lying in the same line of sight when studying distant objects like galaxies. And now in rotation measure synthesis, the major problem that is encountered is radio frequency interference. Now, radio frequency interference, it leads to poor transfer functions when performing REM synthesis, and this will lead to non-uniform sampling patterns, which will cause you a lot of problems in the interpretation of data. In this project, the puzzle that I was trying to solve is how to impute the missing data affected by radio frequency interference. And now, so how do you quantitatively impute the missing data? You need to come up with a mathematical model that could account for radio frequency interference, uneven bandpass weighting, and there are so many other factors which are still unknown, which leads to poor transfer functions. And all these aspects are research challenges, and I don't know what was the underlying model. Now, this is where Gaussian process modeling comes in. Gaussian process modeling demonstrates in a particular way how variables behave. And from this figure, I got it from Royal Transaction Society. It shows the joint probability distribution between two variables, x1 and x2. The solid line shows the marginalized probability distribution, and the ellipse at the center is the joint probability distribution. Now, the ellipse is elongated to a particular direction, which means if you measure the value of x1 and found it to be the value shown by the dotted line, then it means you can more accurately predict the value of x2 shown by the dotted line. And this is the case. This is the case whereby the covariance between different variables, you can control the values of different measures. And this is what I was doing. I selected 10 data points randomly from my training data set. And in the second, the figure on the right, it shows the gray function shows the original function, and the green function is the prediction of the posterior mean, and the shaded area represents the error or uncertainty. And from this figure, you can see some interesting features. And as the uncertainty tries to approach the training data points, the confidence reduces because at those points you know the value there, you know your value there. And now up to this point, I established the methodology that I used in this project, and I needed some data. This is the data set that I used. I used data from data on pulsars. Pulsars are rare types of neutron stars which are seen from the Earth, orbiting spinning at a speed or close to the speed of light. And this data had 17,000 candidates of pulsars. 16,000 of them were affected by RFI, and only 1,600 candidates were the real candidates. And what I did, I selected 500 I selected 500 data points, and in this plot, the gray points they show the gray points are the points now which I selected, and the black points are now the points now with the noise component removed, and the blue function, it shows the blue function shows the prediction of the Gaussian process model. And what I was doing in this project, I was proposing an approach, a Gaussian process approach, as a method of machine learning to mitigate radio frequency interference. Yeah, thank you. That's the end of my presentation.